All right, let's dive into a topic that, trips up a lot of network engineers. How exactly does Cisco ACI, a fabric that famously does not run Spanning Tree, connect safely to all our traditional Layer 2 networks that absolutely depend on it? It's a really important question.
Okay, so here's our roadmap. First, we're going to break down the core problem, the ACI versus STP dilemma. Then we'll get into ACI's really clever solution, this thing called BPDU flooding. After that, we'll look at how this applies in the real world, and more importantly, we'll uncover the really critical configuration traps that can get you into a lot of trouble. And finally, we'll look at ACI's own safety net, its last line of defense.
So let's get right to the heart of it. Before we can even talk about the solutions, we have to understand the fundamental clash here. We're talking about two completely different philosophies for handling Layer 2, especially when it comes to stopping those dreaded network loops.
This is the million-dollar question, isn't it? And it's a huge deal. I mean, for decades, STP has been the protocol that's kept our networks from melting down. So, the answer isn't that ACI just ignores it. No. Instead, it handles it in this very specific and I'd say pretty transparent way.
Here's the most important thing you have to wrap your head around. ACI itself is completely agnostic to Spanning Tree. It's not participating, it's not voting for a root bridge, it's not blocking any of its own ports. The best way to think of the ACI fabric is like one giant intelligent wire. It basically tells the external switches, hey, you guys handle your own loop prevention, I'll just make sure your Spanning Tree messages get where they need to go.
So if ACI is just sitting on the sidelines, how does it actually help the external network do its job? Well, the answer is this core mechanism called BPDU flooding. This is really the magic that lets these two different worlds play nicely together. In a nutshell, ACI basically creates what you can think of as a transparent superhighway for BPDUs. When a BPDU from an outside switch hits an ACI leaf, the fabric's one and only job is to flood that message to every other port that's part of that same logical Layer 2 network. So from the outside looking in, it just looks like all those external switches are plugged into one massive, shared switch.
Okay, let's start with the simplest case. We've got two external switches, S1 and S2, and they're both plugged into the same ACI leaf. When S1 sends out a BPDU for, say, VLAN 2014, the leaf grabs it. ACI knows this is a special frame, so it just forwards it out the other port to S2 as long as it's in the same flooding domain, or FD_VLAN. It's just a simple pass-through, but it's what lets those two switches see each other and figure out their spanning tree roles.
Now, this is where things get really cool. What happens when your switches are on totally different leaves, maybe even in different racks? The BPDU comes into that first leaf, and ACI wraps it up inside a VXLAN packet. It gets tagged with the special identifier, the fabric domain VNID. You see it here as 8896. Think of that VNID like a special postal code that tells the fabric, flood this packet to all the other leaves that care about this Layer 2 domain. For Spanning Tree, it's like all those external switches are just connected by one long invisible cable.
Okay, so now that we've got the theory down, let's see how this works in the messy real world. Because we have to deal with different flavors of Spanning Tree, and as you're about to see, ACI doesn't treat them all exactly the same.
So, when something changes in the external network, like a link goes down, it sends out a topology change notification, or a TCN. It's a signal that paths have changed. ACI is smart. It actually listens for these. With regular Per VLAN Spanning Tree, the TCN has a VLAN tag. ACI sees that and goes, aha, I need to flush my MAC address table for just that VLAN. But with MST, the TCN uses an instance ID, not a VLAN tag. This means you, the engineer, have to manually tell ACI how those MST instances map to your VLAN so it knows which endpoints to clear out when things change.
And this brings us to a huge, and I mean huge, gotcha with MST. MST sends its most important BPDUs, the ones that build the whole loop-free topology, on the untagged native VLAN. Well, guess what? By default, ACI ports don't have a native VLAN. This means you could be silently dropping the very packets that are supposed to prevent a network meltdown. The external switches would never see each other, they'd both start forwarding, and boom, you've got an instant broadcast storm. It's a really dangerous situation. So how do we fix it? Well, thankfully, the solution is pretty straightforward. You have to explicitly configure an endpoint group, an EPG, to act as the native VLAN on those ACI interfaces. You just go into the static port binding and you set the mode to access 802.1p. All that does is tell the leaf switch, hey, it's okay to accept these untagged BPDUs. This makes sure they get processed correctly and flooded across the fabric, and your MST network can finally work the way it's supposed to. And now,
We enter the danger zone. The elegance of this whole BPDU flooding thing absolutely depends on getting the configuration right. And as we're about to see, some small, totally innocent-looking mistakes can have massive consequences.
This is probably the most critical part of this whole discussion. While BPDU flooding is powerful, certain ACI misconfigurations can completely shatter that transparent layer we've been talking about. And when that happens, the external switches, well, they become blind to each other. They each think there's no loop, so they both start forwarding everything, and your network comes to a screeching halt.
Here is a classic textbook mistake. You've got two external switches, both in the same VLAN 20 network, but for whatever reason, they're connected to two different EPGs in ACI. Now here's the killer detail. ACI assigns that internal VXLAN identifier, the VNID, based on a combination of the EPG and the VLAN pool. Since these are different EPGs, they get different VNIDs, even if they're in the same bridge domain. This completely severs the flooding path. The BPDU from switch 1 never ever reaches switch 2. Spanning tree is broken, and you've just created a loop.
And here's another one that's even more subtle, even sneakier. Let's say you use overlapping VLAN pools on the same EPG. This can create a kind of race condition. You see here, Leaf 1 decided to assign VNID 8001 to VLAN 10. But Leaf 2, using a different but overlapping pool, assigned VNID 9010 to the exact same VLAN. The result is the same disaster. The flooding domain is fragmented. BPDUs sent from the left can't get to the right. A loop isn't just possible, it's inevitable.
You know, this is what makes these issues so insidious, so terrifying. Your network might run perfectly fine for months, maybe even years, and then one day you do some routine maintenance, maybe a software upgrade on a leaf switch. The VNID assignment algorithm changes just a tiny bit, and this hidden, latent loop suddenly comes to life and takes down your entire network.
To prevent this specific nightmare scenario, Cisco gives us a really important safety switch. It's a fabric-wide setting called Enforce EPG VLAN Validation. You just turn it on, and ACI will flat out refuse to let you deploy these dangerous overlapping VLAN pool configs. It is one little checkbox that can save you from a catastrophic and, frankly, self-inflicted outage.
But what happens if a loop still occurs? Maybe it's one of the misconfigurations we just talked about, or something else entirely that STP just can't see. For that, ACI has its own built-in bodyguard, the Miscabling Protocol, or MCP. The difference between them is fundamental. STP is passive. It sits around waiting to hear BPDUs from other switches. MCP, on the other hand, is active. It is constantly sending out its own special packets on every single port in an EPG. And if it ever hears its own packet come back on a different port, it knows with 100% certainty there is a loop, and it doesn't care one bit what STP is or isn't doing.
And here is MCP saving the day. We're back in that same bad configuration from before, where the different EPGs broke the BPDU flooding and STP was totally blind. But this time we've got MCP enabled. The leaf on the left sends out its little MCP probe packet. It travels through the external switches, right through the loop, and when it arrives back at the ACI fabric on another port, MCP instantly recognizes its own packet. It knows there's a loop, and it takes immediate decisive action by shutting down the port, protecting the entire fabric.
So the whole process is really simple, but it's incredibly effective. First, you just enable MCP on the EPG you want to protect. The leaf ports then start sending out these active probes. The second a leaf hears its own probe come back, the loop is confirmed. And finally, it takes that port and puts it into an error disabled state, breaking the loop instantly. It's really that last line of defense against misconfigurations or even someone physically plugging a cable in the wrong place.
So we've seen how ACI's modern architecture can cleverly work with a legacy protocol like Spanning Tree, but it also creates this new layer of complexity right at the border. You know, the old world of STP forced us to think about paths and ports and priorities. This new world of ACI forces us to think about policy and VNIDs and flooding domains. It's a powerful shift for sure, but it does leave us with a pretty big question to think about. Is our biggest challenge no longer just building the networks themselves, but safely managing this translation layer between the new and the old?